in the final session in the main room for today, we got 3 speakers talking on the latest topics in verification. Okay, and our first speaker is Niang Hang Hu from the University of Nebraska in Lincoln. He's a graduate student. Is a master's student in computer science at university there, studying under Dr. Lee Song Zhu and Dr. Witawas Shrisian. His research is centered on optimizing testing processes for hardware-based network protocols, aiming to enhance their efficiency and reliability. And he's going to be talking about using symbolic execution to analyze hardware TCP IP stacks based on HLS development. Thank you.
Good afternoon, everyone. I'm Niang Hu. I come from University of the Nebraska Lincoln.
Hang on, no, okay. It probably needs to be higher.
I'm very glad to share my topic about using the symbolic execution to analyze the hardware TCP stack based on the HLS development. And this work is supported by the NFS. What is the hardware TCP stack? The hardware TCP stack refers to the network protocol implemented through hardware. It transfers the network protocol processing functions that are handled by the software on the CPU to FPGA. This method brings numerous benefits. It could improve the system performance, increase the throughput, and reduce the latency. It also reduces the CPU load and the memory resources. But the traditional test method for the hardware TCP stack, it includes 3 steps. First step is concrete test packets. Next, send the test package to the test device. And then we will compare the result with the expected outcomes to identify the issue. The test approach includes the manual test and the random test. But right now, the hardware TCP stack is very complex, and the hardware test includes a lot of process. My paper is focused on the function test, not focused on the the logical test and the timing test. So for the hardware TCP stack, it's very complex for the TCP header. It includes a lot of bits and includes a lot of different scenarios. We need to create a lot of test packages to cover all the conditions. When you use this manual test or the random test, it's difficult to cover all the conditions. Based on this, we propose the symbolic execution to test the hardware TCP stack. What is a symbolic execution? Symbolic execution is a common method in the traditional software testing. We select the CLI as our test tools. What is a CLI? CLI is based on the symbolic execution used for testing the C and C++ program. And this benefit of the CLI, it could is about to detect the errors, vulnerabilities, and the boundary conditions about the program. When we use the CLI to analyze the symbolic function. Like, you know, the read is a, we suppose the read is a symbolic function. And this is symbolic function. We could set the x is a symbolic variable. If x is symbolic variable, we could use a CLI to analyze the read function and explore all the read functions execution passes. The read function includes 3 branches. The CLI could create the 3 test cases based on the 3 branches. And these test cases could get the result what we want, because it helps us to save the test time. This test time we have the project, we have the target to create. It's like this 3 branch. For the hardware TCP stack, we compare the 3 methods about the manual testing, random testing, and symbolic testing. The manual testing, we need to test a lot of conditions, and it also depends on our experience. The random testing, we need to create a lot of numerous test cases, but the test cases is not uncertainty. But the symbolic execution includes the 3 passes, will cover all the conditions. It will save a lot of time. This is a chat flow about the CLI, how it's used to test the hardware TCP test. First, we could know the hardware TCP stack is implemented in C and C++ language based on the HLS technology. What's the HLS technology? HLS technology is a high-level surface technology, high-level surface development tools. It could help us to transfer the traditional C and C++ to the low-level hardware language. Next, you know, we use the C-lang compiler, the source code, because the source code is based on the C and C++. And the C-lang language, C-lang compiler will compile the source code and transfer the source code to the intermediate files. The intermediate files we could use the CLI to analyze the intermediate files to generate the test cases. These test cases will transfer to the solver. This is the solver, and we get the result from the solver. We base the result from the solver to generate the test cases. And these test cases will cover all the execution passes like true or false. When we use the CLI to analyze the hardware TCP stack, we meet several challenges. First, you know, the CLI is the traditional test cases for the software, but the hardware TCP stack is special. The CLI does not support the data type. This data type includes the high-level surfaces. Next, you know, some functions the CLI also does not support. And the last one is the concurrent computation. The solution 1, we use the basic data type to construct the special data type. You know, the basic data type includes several choices, and the basic data type is like this, and W, it means the special data types, the bit width about the special data type. It's from 1 to 4096. How can we use the basic data type to transfer to the special data type? We need to follow these principles, because these principles could help us let the CLI to know what's the data. First, we need to maintain the range of the data value, because we use the traditional data type to transfer to the special data type. Sometimes we will out of the range, because when we define a special variable, the data width is 1 bit. If we use the basic data type to transfer the special data type, we will large the access scope. Next, we need to select the appropriate basic data type, because we have a lot of basic steps. Which one is best? Next, we need to optimize the memory space, because the memory space, when we create the test cases, we will create a lot of memory variable. So we need to save the memory space. And last one, we need to short the test cases, because if we create a lot of execution passes, we need to spend a long time to transfer to the server. The server will resolve every issue. So that's why we need to spend a long time. This is the example. This is the first example. How could we create a special data type? First, we define a special data type. The data width is just 1 bit, and the data range is from 0 to 1. We use the enzyme chain to transfer the data to the special data type, but the enzyme chain data type is bigger than the special data type. So we need to limit the access range. This is limited the access range. Based on this, let them have the same scope of the data value. This is another example. This special variable has a long bit width. It's 130. And the data range is very big. How could we fix this issue? We need to create 3 symbolic variables. First, create 2 symbolic variable. It's unsigned long. Every variable is 64 bits. But the 64 bits is not match the special variable. So we need to add another variable, another basic variable, like unsigned chair data. And the last one, we also need to limit the access range. Okay, the solution 2 unsupports the function of the HLS. When we use the CLI to analyze the high-level synthesis source code, we will meet several issues like this. Some function the CLI does not support. We need to re-implement the source code. Let the CLI to know what's the function, how code works. And the issue 3, the high-level synthesis has some feature like a multi-thread task. When we use the multi-thread task, the CLI is limited to support the concurrent computation. We need to convert the parallel to the ones. And like based on this, we could like this high-level synopsis module run this high-level run this TCP header. We do the experiment to test which one is best. Why we take this? Because you know there are a lot of basic data types. Which one is the best to construct the special data type? We do a lot of experiments to test which one is the best. First, we need to consider the optimize the testing time. Next, we need to consider the memory space. When we calculate when we use the unsigned chair to create the data type, because you know the data type is the range is very small. When we use the long data type, it's very big. And if we use a small one, we could create a lot of symbolic object. If we use the long data, we could the smaller symbolic objects. This could save the time. No, this could save the space memory, but this could save the time because you know the symbolic variable is very less. Based on this experiment, we get the result is that you know if we want to save the time, we need to create less symbolic variable and need to match the length of the special data types. The conclusion, we modify the HLS library so that the CLI could work on these projects. And the next step, we want to test the whole project source coverage, because you know because this is a hardware TCP stack is a little bit big. We test all the function. You know, spend a long time. And the last one, we need to optimize the symbolic execution, because the symbolic execution needs to spend a lot of time and a lot of memory. That's why the first, you know, the first test coverage we didn't get it, because we need to, you know, if the project is big, we need to create a lot of execution passes.
Okay, thank you.